with those, we explained the design of the material filter in two methods. Now we're going to go to hydraulics. After we design the geometrical size, we design the filter material, then we should design the pipe. As we said, I'm sorry about this picture, this pipe, the above part should be perforated or slotted to allow the flow of seepage to enter the pipe, but the bottom half of the pipe should not be perforated, it should kept solid, and it's going to work as the capacity to hold the flow. Now, this type of flow is open channel flow. And for open channel flow, the hydraulics equations here works, specifically Manning equation. I'm going to go to the slide to show Manning equation. So it is the Q, C, the capacity. That means the flow that the pipe can hold.
So QC is one term.
Yes, QC, capacity flow, equal over N. Now, what is N? This is Manning roughness coefficient. It depends on the type of the pipe. So if you want to select a pipe and you go to the company page, you download the table, give you the diameters, different diameters that are available commercially, and give you the N value. Usually the companies that produces pipes, they do their experiment and evaluating the N value for their pipes. Manning roughness coefficient. The smoother the pipe, the lower this. So the value.
So it is usually a value greater than 1.
No, the N value 0.01, 0.02, 0.05. But usually the value of the N. But if you have like an N value.
What if you have a completely smooth pipe?
Oh, there is nothing in reality called completely smooth. Okay, but you mean very, very smooth. Then the value of N can reach 0.001. So those companies, what they usually do, they have small labs. They produce the pipe and they put it in a certain slope, and they run the flow with a flow meter so they can measure the real flow and use the QC, this equation with the real flow that is measured, and they obtain the N values, and they repeat it for different pipes and give you the average N value.
So if A is the area of the cross section, or is it the area of the flow?
A is the area of the flow.
Area of the flow.
Yes.
How about R? Is it the radius?
We are going to explain. R is the hydraulic radius. All right.
Hydraulic radius.
Which we're going to explain now.
Okay.
And S is the longitudinal slope.
How much usually we give a slope to a pipe?
Okay. Usually 1 in 100 or 1 in 1,000, depends on the diameters of the pipe. The smaller the diameter, you give more slope.
Okay.
Is the capacity. So there are tables that give you the recommended. Usually when we design, if the embankment has a longitudinal slope, we should go with the slope of the embankment. However, to have a homogeneous depth of soil over the pipe. So when you think about how much the pressure the pipe can hold, I mean the soil pressure, then you're going to have a uniform soil pressure over there if you slope it the same. But hydraulically, the slope affecting the velocity and affecting the Froude number. Now, Froude number is a critical point in designing pipes, because we have to make sure that the Froude number is not over 1, greater than 1. Otherwise, there will be a hydraulic jump in the pipe, and we should avoid that. So first trial, we're going to go with the slope of the embankment, make it parallel, if the embankment has longitudinal slope. Do you know what I mean?
Yeah, but usually they don't.
Okay, in this case, we're going to have a mild slope at the beginning, okay? And maybe for a mild slope, you're going to get a big diameter. Then you're going to increase a little the slope. But we are talking about 1 in 100, 1 in 1,000 range, from 1 in 1,000 to 1 in 100. 1 in 100 is a steep slope for such cases.
Okay.
All right.
Okay.
So let me get back to the, sorry. Here's the area. So pi over 4, but divided by 2, because we are using what? We are using half the area. Okay, because we said the top part will not work as a capacity flow. It's going to work as, because it is perforated, so it's going to work just for allowing the seepage flow to come inside. The capacity is only for the bottom half of the pipe. Now R is called the hydraulic radius, which is A over P, where P is called the wetted perimeter. You see the red?
Yeah.
So that means the contact of the water with the boundaries of the pipe, the perimeter, wetted perimeter. So with this, we're going to have dP over 4 as the hydraulic radius. So after you plug those values, this gives you QC. That means what? The capacity of the flow. Now,
you mean pipe capacity, right?
exactly. The pipe.
This much you can allow through that pipe.
Exactly. With this given diameter, with this given type of pipe, that means N, it's gonna transfer on a half level this capacity of the flow.
So you're calculating everything based on the half level.
Yes, exactly. Now, Q, how much flow will gonna come here from the seepage? Is a Q small, the seepage per unit length, times W. I'm gonna get back to this equation. Do you remember? Q is the seepage flow per unit length multiplied by W.
Now, what's W?
Okay, I'm gonna go back, show you W that I showed before. This is the W.
Oh, okay. Okay.
Because
it's
this,
yeah. It's the length of the collector pipe.
exactly.
Okay.
All right. Getting back here. Now, if QC less than Q, that means
we're okay. Sorry, we're not okay.
Yeah. So look at step 3 here. So we have to choose what? Let me get back. So step 1, starting with the smallest commercially available drain pipe. Yeah. So you have the diameter, you can calculate the area, and you can calculate what? The hydraulic radius for diameter. Then you can what? Adopt a value of longitudinal slope, S, which should be close to the embankment longitudinal slope, if any.
Okay.
If not, then you're going to start with a slope of 1 to 1,000, 0.001, which is a very mild slope. And after that, you calculate the capacity using Manning equation after deciding the N value. Now, if QC less than Q, that means this pipe cannot hold the seepage flow. So we're going to jump to the next biggest diameter available. For example, if the minimum diameter is 4 inches, and we get this, then we have to go to 6 inches maybe, or 5 inches, okay, according to the available diameter. If, on the other hand, if Q, the seepage flow, that means the flow that this pipe gonna receive, is less than the half capacity, then that means the pipe will run not at the half, lower. The water level will be lower. Is that clear, doctor?
Yeah.
Okay. In this case, we should go to those calculations. If QC greater than Q, we should go to this diagram, which is well known in hydraulics. They call it the partial flow diagram. So Q over Q full. This diagram based on Q partial flow. That means when a pipe running in a partial flow, like this in the figure, the water is not covering or filling the whole cross section, over Q full when it is all full. So Y over D, Y is the same as H here, which is the real depth of water, while D is the diameter of the pipe. Okay?
Yeah.
And we're going to see why we should do this. So the step here, we should find a Q over a Q full. Now remember, we calculate a QC based on half of the pipe. Now, this diagram is based on a full flow. So the Q full is 2 QC. We don't need to recalculate. Why? Because for the full flow, I'm going to get back to explain this. For a full flow, the hydraulic radius will be the same because the area will be multiplied by 2 and the wetted perimeter will multiply it by 2. So dP over 4 is the same for half flow or full flow. The only change in Manning equation is the area for a full flow. And instead of divided by 8, it's going to be divided by 4, pi d squared over 4. And that means Q full will be QC multiplied by 2 because only the area will be multiplied by 2. Clear, doctor?
I'm not sure of one thing. Can we go back one step?
Yes.
So
now,
this D in the equation of A.
Yes.
There is D and the small p, D sub p.
Yeah, D pipe means D pipe, the commercial diameter of the pipe.
So it's making me confused when you have another P in the second equation, which is the capital P.
Oh, this capital P is the wetted perimeter.
Yes. So when I was looking to the first equation, I thought that we have a diameter, then we have the perimeter squared.
Oh, no. I'm sorry about that.
So this is simple pi d squared over 8.
Exactly.
So pi d squared over 4 is the full area, and divided by 2 makes it divided by 8.
Exactly. So
so that's half of the area of the pipe.
Exactly. Now, if you
then,
have
then why you are dividing it by perimeter again? Because it's easy to find out the radius. It's dp over 4, so it's half of the total. Okay.
Look, here R is pi d squared over what? 8. Which
over 8.
Yeah. And here pi d is the whole perimeter divided by 2.
I just got confused between the two p's.
Okay, I'm sorry about that.
No, it's fine. I understand now.
You got it? Now.
Yeah. So dp is one term and refers to the diameter, while the capital P is the perimeter, which is also diameter multiplied by pi divided by 2.
But it's a perimeter. P is a perimeter.
For this case, when we have half of the pipe is full, it's also related to diameter very easily. So it's d multiplied by pi divided by 2.
Exactly.
Okay.
Now,
but what happens when you have less flow?
Okay. Yeah. But before that, what happens when we have full flow?
So it will take the full perimeter.
Yeah. Does R changes? No, because the area will multiply by 2 and the perimeter will multiply by 2.
Oh,
so,
yeah. You're right. The definition of R will remain the same. Is the diameter divided by 4.
Excellent. But the area, what?
The area will go higher, of course.
And multiplied by 2, correct?
Yeah.
So when we go to this equation, before we used half the area and the hydraulic radius, we calculate QC, which is the capacity for half flow. Now, if we need to calculate Q when the pipe is full, we don't need to repeat this. We just need to multiply the area by 2. And that means Q full is double QC.
Okay.
Okay.
Yeah.
Why I'm calculating Q full? Because this diagram depends or based on Q over Q full. Okay. So here you see the step Q divided by Q full, it's going to be Q over 2 QC. So when I find the ratio, for example, let's say I find it to be 0.4. We're going to see this in the example. So I'm going to go horizontally to the curve of the Q and go down.
Let's move.
All right. And finding what Y over D.
So why represents here the H?
Oh, to be honest, this figure was copied from a textbook, which he names the Y as H. That's why I added here H equal to Y.
Okay.
All right.
So the x-axis is H over D, and the y-axis is on the left side.
Yes.
Will give me what?
Either Q over Q full or V over V full.
Oh. So it's a ratio. Okay. And on the right side, there's a small curve measurement that is N over M full.
Yes. So sometimes, theoretically, the N value is also affected whether you have a partial flow like this or a full flow. But usually in design, because as you see, the ratio is not that, the variation is not that high. So we assume that N partial equal the N full. So we ignore this curve.
Okay.
If you want to be more precise, you can go.
Is it on the conservative side?
Exactly.
Okay.
All right. So you know why it is in the conservative sides? Why?
I think we will get N and apply it to the equation.
Yes, exactly.
And N is in the denominator.
Exactly.
Okay.
All right. So now, after I find Y or H, I can find all of those. You see those? I can find theta. Why finding theta? We're going to see. Okay. And then I can find A. Now, this A is not the previous A. This is the A of the partial flow. Correct? And P, this is all before what we calculated here. A and P are for what? For a very easy half flow.
Half of the circle, yes.
While since we have Q less than QC referring to half the circle.
Yes.
But we have a Q less, so we're gonna have a depth of water below the half. How much is this depth? That's what we have calculated using this figure as well. Okay. Now for this one,
this figure originally is found in the Navy's design manual or what? What?
This figure usually found in any hydraulic textbook, in textbooks of design of
flow in pipes.
Yeah, flow in pipes. Yes.
Okay.
Okay. So in this case, after I find the real depth of water, then I can find the real area of the water and the real wetted perimeter and the real RH, hydraulic. Yes. Okay? Clear?
Yeah.
Okay. Now, also from this equation, I can find T, the top width. I can explain why we are finding all those variables.
Yeah, why are you interested in T?
Yes, because a Froude number, which should be checked, is V, the velocity of flow, based on what? On the partial flow. When we have a depth less than half the depth of the pipe. And DH, okay, here again, I'm sorry about that. This is not D times H. This is one term, DH, which is called the hydraulic depth, is the top width divided, sorry, the area of the flow divided by the top width. So when you find DH and you find T and you find RH and you find A, okay, you can find V, the velocity of the flow, when you have partial flow, and then you can find Froude number. Now, if this Froude number is less than 1, we are okay. If this Froude number is greater than 1, that means we have supercritical flow. And when we have supercritical flow inside the pipe, there is possibility of a hydraulic jump, which we don't want to have through the pipe. So if the Froude number is greater than 1, we should get back and reduce the slope or increase the diameter of the pipe.
So your safety factor, let's say, your safety factor is in increasing the pipe diameter.
I just want to avoid any supercritical flow. When we have a Froude number greater than 1, that means we have supercritical flow. And this is not allowed in pipe flow because it may develop a hydraulic jump. And you know, hydraulic jump means disturbance in flow, vibration in the pipe, all of those things, which we should. Yeah. So if you calculated FR.
So if we calculated and it was not less than 1, what shall we do?
We get back and repeat the process by decreasing S, the slope, because with the longitudinal slope play a very high role in the velocity. Okay?
Yeah.
And the other option is to increase the pipe diameter. When you increase the pipe diameter, also this will increase T, the top width. Okay? And this reduces, increase A, increase T, but this will increase DH, the hydraulic depth, and this will reduce the Froude number. So by reducing V, how we reduce V? By decreasing S, longitudinal slope, or by increasing DH, the hydraulic depth. How we increase the DH? By increasing the diameter. When you increase the diameter, A will increase substantially, T is also increased, but DH, as a result of this, DH will be increased.
And what is this DH? Is it a one term or D times H?
No. It's, as I told you, it's one term. DH is one term, which is called the hydraulic depth.
Okay.
Which is the area divided by the area of the flow divided by the top width. Okay?
Yeah.
So by this, we designed everything, the pipe and the filter. And here is an example. Okay? So we'll go through the example. Do you like to go through the example or not?
It's up to you.
Okay. So, okay?
Yeah.
All right. So
this is a recorded video, so you can take your time.
Okay.
People can watch it by parts. It doesn't matter. Yeah.
All right. Thank you very much. So let me move this away. Okay, put it here now. All right. So this is the embankment we have. We have height of the water at the upstream is 32 meters. The upstream side slope of the embankment is similar to downstream, 1/2, when vertical to 2 horizontal, when vertical to 2 horizontal. The top width B is 7. And the height of the embankment total is 35. So HE is 35, H is 32, alpha, beta, and alpha are the angles, which is arctan 1/2, and B is 7 meters. So this is the geometry that we have. Now, soil properties of the embankment. The hydraulic conductivity is 4 times 10 to minus 4 millimeter per second, and D10 of the soil is 0.11, D15 is 0.18 millimeters, D50, D60, all of those data. And the angle of repose of the soil is 30 degrees. Now, the adopted longitudinal slope of the embankment is 0.001, and the drain pipe spacing exit is 60 meters. So W is 60, that means the length of the pipe, where we finish the pipe and start a new pipe by directing the flow to the side as shown in the previous figures. And we assume that the embankment has a slope of 0.001. If it doesn't, then we can adopt a slope 0.001 for the pipe and check if the design of the pipe will check or not. The available drain pipe minimum diameter is 3 inches with Manning's N 0.014, perforated pipe with perforation holes diameter 0.5 centimeter. So we have all of these collected data for the design. And this is to show again a clear the value of the soil of the embankment, and we require to design the filter. Any question, Doctor?
No, the input data are clear.
Okay. All right, so we're going to start with the first step is designing the size of the filter. So from the data, we have the height of the embankment, 35 meters. H, the height of the water, 32 meter. Tan alpha and tan beta is 1/2. If you remember the slopes from both sides, upstream, downstream, the same. And B was 7 meters, so we're going to apply the equation for D, and that gives me D equal 102.2 meters, the horizontal distance to the theoretical start of the ferritic surface. With the D value going to the equation, Dupuy equation for the seepage phase L, plug in the values, we get L to be 25.18 meters. Any questions so far?
No, I think it's clear.
Clear. Okay. Now, after finding L, we can find the seepage flow. This is the equation for the seepage flow. And plugging in the K value. Now, if you remember, the K was 4 times 10 to minus 4. We change it to meter by dividing by 1,000. And we have L 25.179, and we have tan alpha and sine alpha, and that's give me the Q value 22.52 times 10 to minus 7 meter cube per second per meter perpendicular or per meter length of the embankment.
Yeah.
All right. Going to the geometrical equations to define the filter. So the filter here adopted the inclined part equal to L, which is 25.18. And here we have L1 plus L2, and this is H as we defined it before. So using geometrical equations, we can find H and L1 and L2. I think this is very easy to follow. So the total 22.521 plus 19.503 comes to 42 meters. This is the filter dimensions. And the slope here is equal to 5. We selected the slope here equal to 5. So we have a big...
The pipe diameters, because they are pre-manufactured.
Yes.
So they're chosen from catalogs or something.
Yes. So
when you use any diameter, you have the safety decided already for you. It's like you have a certain flow and capacity. So there's no meaning of changing the pipe diameter to a lesser one or a higher one, because when you reach to one pipe diameter that gives you enough capacity and the flow quantity ratio,
yeah.
That will give you some margin, let's say.
But Doctor, we didn't yet went to the pipe flow. Now we are just designing the size of the filter geometrically. So the 42 meter is the distance here.
I'm trying to summarize what I want to get and where to find my safety, my margin.
Yeah.
My margin is the target for me. I'm asking that. Yani. I want to know where to investigate my margin.
Uh, margin of the pipe or what?
No, I'm designing a filter, right?
Right.
So this filter has margin in materials, margin in geometry, and margin in pipe.
Yes. Now we are in the stage of geometry.
So geometry is simple.
Okay.
As long as you're using the face as one of the dimensions of the filter, you have the margin.
Exactly.
Because certainly you can go lower than that.
All
And
right.
the second one is the filter material.
Yes. Here are the filter materials. So
Okay.
yeah. So I decided to use the US Navy method because it involves so many conditions. So first I have to check CU because if you remember,
Yeah, we need CU in the equations.
Yeah. So we are lucky. Yeah. Because the CU is not less than 1.5, so this limit should not be increased to 6, and nor greater than 4, so this limit do not need to increase to 40.
Okay.
All right. So in this case, we apply this equation. So D15 filter should be less than 5 D85, so it's going to be less than 1.7 millimeter. And similarly, these two conditions, we applied the data that we have for the soil. If you remember D50 of the soil, the embankment soil is 0.21 millimeter. So D50 filter should be less than 5.25 millimeter. D15 filter should be less than 3.6, but here we see that this control, because already we have from the first condition, D15 filter should be less than 1.7. Here we have it less than 3.6, so less than 1.7 will control, will govern. Other conditions, okay, D15F for avoiding build-up. Also, we get 0.72. So D15F has three values. Should be greater than 0.72 here in the summary, and less than 1.7 or 3.6. Of course, the 1.7 will govern. So D15 filter should be between 0.72 millimeters and 1.7 millimeter. And D50 from the previous condition should be less than 5.25. And finally, D85 of the filter greater than 1.2 the whole diameter. And if you remember, we have it 0.5 centimeter, the perforation diameter, that means 5 millimeters. So that means D85F is should be greater than 6 millimeters. Okay.
So can you explain why do you have three ranges here?
Okay. For D15?
No, I see three dotted ranges.
Oh, okay. This is the show that you can create a margin or an envelope for accepting the filter material. If
So
you're
which one of these is going to be true for me?
okay, so a filter 1 to protect the base soil range in curve A, a filter 2 to protect filter 1. So this figure is when we have like more than one filter, like a successive filter. So I'm sorry, it's not related. It's just showing that we can develop an envelope for checking those values. But those are the most values that we should check, D50, D85. Let me get back to more clear one. Okay, so this is how we develop for a single filter, the envelope where we accept the filter.
Okay.
So
when you have layered filters, you're
yes,
using each layer as a soil for the next one.
exactly. Yeah, here it is, A, B, and C.
That's why you have here 3 ranges of 3 gradation curves for each layer of the filter.
Exactly. Thank you for this good comment. So that's good. I see.
You're welcome.
Oh, we took a long time. I'm sorry about that, but you're still concentrating. All right. So yeah, that's intelligent people, what they do. Okay.
It's good we're not sleeping.
Yeah. I hope it was also interesting, right?
I'm very interested, but when you talk a lot of numbers, I get sleepy.
Oh, so
No,
okay.
I'm
All right.
joking. It's a wonderful thing to
Oh,
understand. The principles are more important for me. We can find these equations elsewhere, but
yeah.
to gather all these principles in one single uh, recording or one single lecture, that's the important part, because you're you're gathering the links that will complete the chain of the design.
That's a very important point that I always have a discussion about with engineers and professors of engineering. The most important thing that how you when you have the basic courses you studied knowledge in fluid, knowledge in strength
Yeah,
of steel or deformable bodies, soil mechanics, how you connect between them to create a topic that have multiple, you know, because here we have something from geotechnic and something from hydraulics, and we connect those knowledges to create something. Correct? Design. Yeah.
that's what usually it's not easy to find this type of stepping in 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 like soil mechanics lectures or hydraulic flow lectures. You there you will usually concentrate on a single phenomenon, and you discuss it theoretically, and you find its equations and what controls it, but you will never relate it to a complete design.
Right.
Uh,
Right.
we know what's the filter requirements, but
Yeah.
how to establish the whole thing, geometry, flow. Of course, starts with the flow net, with the deputy theory. Then you end with the pipe size. You end with the filter material. You end with the filter geometry. You know your margins. You know what materials you're buying from the market. How you're getting the fruit number or the Manning's number. It, I like it. In fact, I believe it will be very useful for the practicing engineers.
Yeah, that's exactly my idea is to create a full engineering problem that you need just what we have worked before together when we do like a real design. You take the part of geotechnic and I take the part of hydraulics, and then we integrate both to reach to a full design. Correct?
Yeah, I used your water pressure in dynamic conditions on the stability of Mosul Dam.
Yeah.
I still don't I still don't know how you got them. I know how to get water pressure uh, from well, if you have a pseudo static method, I know how to get them, but your figures were more reliable than when we used them for this stability analysis of Mosul Dam.
Yeah, I remember at that time I used finite element analysis.
So you did finite element, and I did something like find differences in slope stability.
Yeah.
And at the end, it's as you said, we're linking many parts of engineering in one major problem solution.
Right, right. Yeah, that's the things, when you be multidisciplinary, you can connect those things. That's the advantage of multidisciplinary. However, it has a big disadvantages. All right, so here's the Q, which is the seepage flow. That means the flow that expected to come from the soil body, and that the pipe we're going to design should be capable of holding this flow. So going with the same steps, we took the area of half the pipe, the hydraulic radius, assuming half of the pipe, plug them into Manning equation, we get QC, the capacity of this pipe, of our drain pipe. As you see here, it's half the flow. But really what happened in our design, it's not necessarily that we're going to get the flow up to half. Should be less or equal half. Less or equal. So how we know that? We're going to go, so we get this QC, and the Q full, if you remember, is 2 times this. Because so we need the Q full. So Q, the seepage flow, divided by 2 times QC, which is the Q full, we get it 0.192. Now coming to 0.192 and coming to this curve, go down, we read Y over D to be like 0.35. Okay. By the way, I made one of my students to digitize this curve, and I find regression equations for these curves, and the regression determination coefficient was very high, like 0.98, 0.99. So usually when I do like designs with programming, I use the equations rather than the curve. Equations give you, if I use the equation and you use the equation, you're going to get the same number. But for me, I read this to be 0.35. You may read it to be 0.34, correct? So
yes, of course.
Yeah. So that yeah.
We're digitizing almost every curve these days. One question I have here for Q full or Q. Where are you laying the pipe exactly? How do you assume that the whole seepage flow from the embankment is going to that pipe?
Because we are assuming two-dimensional flow. All of these are two-dimensional flow.
I understand, but are you really assuming that all the flow will go to that pipe?
Yes.
So are you putting the pipe like at the bottom of the...
Exactly. It is inside the filter. I'm going to show you.
It is inside, but is it in the bottom part of the filter?
Yes, in the bottom pipe of the part of the filter, exactly. Oh, sorry.
So why don't you allow then the slots or perforated holes at the side in the flow face, in the part facing the flow?
You know better than me. Water always when seeps, it's gonna go to the easy ways, right? So wherever you put the slots or the perforation, for example, if you put it like the filter at the top a little bit, I mean the pipe, sorry, if you put in the top, so automatically when the water coming in the bottom and faced with this solid particle, it's gonna build up to go to the perforation and go through the perforation. So you're right. Maybe a better to put the, and I cannot put it on the left half, the perforation, because how can I transfer the flow perpendicularly? Do you know what I'm saying? Okay.
I'm assuming you're right, but I
Not
assume also that
repeat your
location of pipe may allow different locations of the holes.
You mean location of the pipe in the filter? It is here.
Yes.
It usually be at the bottom of the filter.
How do you assume that the water will flow completely to the pipe and it will not pass below or above it?
Because automatically when you have perforation, then there will be what? A low head.
So you're assuming this is the easiest way for the flow, so the water will not search for another one.
Exactly. The water always will follow its way to the scientifically when you have
Of course, this has less permeability, and this has more permeability, so it will go to the one having more permeability. But in fact, even the less permeability will get something if you calculate correctly.
Definitely, you're right. But this is not too much to have, and eventually most of the flow will go through the perforation. Yeah, I have seen a filters like a top filter, like with the pipes at the most bottom, and the half below the solid even go below. You get my point?
Yeah, it's even below the filter.
Below the filter. So like
it makes more sense. Yeah.
Yes. So the perforated top half is actually matches the horizontal line. The center line of the limit of the perforation is within the horizontal line.
Okay, let's finish this. Let's go to the last slide.
All right. Okay, so we are here. Okay, so with this, all of those calculations, y over d, theta, and area of flow, PF, the wattage perimeter of the real flow, partial flow, and then we calculated the Froude number, as we explained before. So we got it 0.256, which is less than 1. That means our design is okay, and we will never have a hydraulic jump.
Perfect.
Thank you very much.
We thank you, Doctor. You were great, and I really appreciate your presentation with us. It will give a great value to the channel and to the videos of this GeoGuides series. And I hope I'll see you again in this some way. Maybe I can convince you with another subject someday.
Yes, hopefully. It's my pleasure to have you. And
so that's the end of the presentation today. And the last thing we tell you, Professor Suhily, good night. It's late, and it's time to sleep now.
Thank you very much to have you, and thank you for your comments. Hope to see you again in another presentation.
I hope so. Good night. Bye-bye.